Induction foundry and heat treatment are essential processes in modern manufacturing. They involve the use of heat to melt and modify the properties of metals. These techniques are crucial for producing a wide range of components, from engine blocks to surgical instruments. Understanding these processes is key to appreciating their impact on various industries. Imagine a blacksmith shaping metal over a fire. Induction foundry and heat treatment achieve similar results, but with greater precision and control. These techniques utilize electromagnetic induction to heat metals selectively and efficiently. This controlled heating allows manufacturers to achieve desired material properties such as strength, hardness, and ductility. Induction foundry focuses on melting metals, while heat treatment alters the properties of solid metals without melting them. Both processes are interconnected and play vital roles in manufacturing. They offer significant advantages over traditional methods, including faster heating rates, improved energy efficiency, and reduced environmental impact. This exploration delves deeper into the principles, applications, and future trends of induction, foundry, and heat treatment. By understanding these processes, we gain insights into the fascinating world of materials science and its impact on our daily lives. Induction heating relies on the fascinating principles of electromagnetism. It involves using an alternating current to generate a magnetic field that induces heat within a conductive material. To visualize this, imagine a copper wire wrapped around a metal object. When alternating current flows through the coil, it creates a fluctuating magnetic field. This field penetrates the metal object and induces eddy currents within it. These eddy currents encounter resistance as they flow through the material, generating heat. The heat generated is proportional to the frequency of the alternating current and the strength of the magnetic field. This method of heating offers several advantages. Firstly, it allows for contactless heating, reducing the risk of contamination and oxidation. Secondly, the heat is generated directly within the material, resulting in rapid and efficient heating. Lastly, induction heating allows for precise control over the heating process, enabling manufacturers to achieve specific temperature profiles. The frequency of the alternating current plays a crucial role in determining the depth of heating. High-frequency currents generate heat in a shallow layer near the surface, ideal for surface hardening applications. Low-frequency currents penetrate deeper into the material, making them suitable for melting large volumes of metal. Induction heating has revolutionized metal casting processes in foundries worldwide. Unlike traditional furnaces that rely on combustion, induction furnaces utilize electromagnetic induction to melt metals with remarkable efficiency. This section explores the applications of induction heating in foundry work. In an induction furnace, a crucible containing the metal charge is surrounded by an induction coil. When high-frequency alternating current flows through the coil, it induces eddy currents within the metal charge, rapidly heating and melting it. The molten metal can then be poured into molds to create various shapes and sizes. One of the key advantages of induction furnaces is their ability to melt metals without direct contact with the heat source. This eliminates the risk of contamination from combustion byproducts, resulting in higher purity metal castings. Additionally, induction furnaces offer precise temperature control, ensuring consistent melt quality. Induction heating is also employed in other foundry processes, such as holding furnaces for maintaining molten metal at a specific temperature and preheating molds to improve casting quality. The versatility and efficiency of induction heating have made it an indispensable tool in modern foundry operations. Heat treatment encompasses a range of controlled heating and cooling processes used to alter the physical and mechanical properties of metals. These processes involve heating the metal to a specific temperature and then cooling it at a controlled rate to achieve the desired microstructure and, consequently, the desired properties. One common heat treatment process is annealing. Annealing involves heating the metal to a specific temperature and then slowly cooling it, often in a furnace. This process softens the metal, relieves internal stresses and increases its ductility, making it easier to machine or form. Hardening, on the other hand, aims to increase the hardness and strength of a metal. It involves heating the metal to a specific temperature and then rapidly cooling it by quenching it in water, oil, or a specialized polymer solution. This rapid cooling traps carbon atoms within the metal's crystal structure, making it harder but also more brittle. Tempering is often performed after hardening to reduce the brittleness induced by the hardening process. It involves heating the hardened metal to a lower temperature than the hardening temperature, and then allowing it to cool. This process helps to relieve internal stresses and improve the toughness of the metal. Section 5. The significance of temperature control. Precise temperature control is paramount in both induction heating and heat treatment processes. The rate of heating and cooling, as well as the time spent at a specific temperature, directly influence the final properties of the metal. Understanding the importance of temperature control is crucial for achieving consistent and desirable outcomes. During heating, the metal undergoes various phase transformations at specific temperatures. These transformations affect the arrangement of atoms within the metal's crystal structure, ultimately influencing its properties. Precise temperature control ensures that the metal reaches the desired phase for the intended application. Cooling rates are equally critical. Rapid cooling, such as quenching, can trap atoms in a metastable state, resulting in increased hardness but also increased brittleness. Slower cooling rates allow for more time for atoms to rearrange, leading to improved ductility and toughness. To ensure precise temperature control, modern induction heating and heat treatment systems utilize sophisticated sensors and control systems. These systems monitor temperatures in real time, automatically adjusting heating and cooling rates to maintain the desired temperature profile throughout the process. Section 6. Real-world applications of induction and heat treatment. The applications of induction heating and heat treatment are vast and diverse, spanning numerous industries. From automotive to aerospace, these processes play a crucial role in manufacturing a wide array of components that we rely on daily. In the automotive industry, induction hardening is commonly used to harden gears, crankshafts, and other components subjected to high stress and wear. This process enhances their strength and durability, extending their lifespan and improving vehicle performance. The aerospace industry relies heavily on heat treatment to achieve the exceptional strength-to-weight ratios required for aircraft components. Heat-treated aluminum alloys, for instance, offer the necessary strength and lightweight properties for aircraft wings and fuselages. Other notable applications include induction brazing, which involves joining metal components using a filler metal that melts at a lower temperature than the base metals. Induction soldering is similar to brazing, but uses a filler metal with an even lower melting point. The heat treatment of cutting tools enhances the hardness and wear resistance of tools used in machining operations. Additionally, the heat treatment of medical implants ensures the biocompatibility and longevity of implants used in the human body. Section 7. Challenges and solutions in induction and heat treatment. While induction heating and heat treatment offer numerous advantages, some challenges are associated with these processes. Understanding these challenges and their solutions is crucial for optimizing process efficiency and ensuring product quality. One challenge is the potential for uneven heating, especially in complex-shaped components. This can lead to inconsistent material properties and potential defects. To mitigate this, manufacturers employ advanced coil designs and computer simulations to optimize the magnetic field distribution, ensuring uniform heating patterns. Another challenge is the risk of overheating, which can lead to material degradation or distortion. This is particularly critical in heat treatment processes where precise temperature control is paramount. Modern systems utilize sophisticated temperature sensors and feedback mechanisms to prevent overheating and maintain the desired temperature profiles. The selection of appropriate quenching media and cooling rates is also crucial. Improper quenching can lead to cracking, warping, or undesirable microstructures. Manufacturers carefully select quenching media based on the material being treated and the desired properties. Section 8. A glimpse into the history of induction and heat treatment. The roots of induction heating and heat treatment can be traced back centuries, with early civilizations utilizing rudimentary forms of heat treatment to enhance the properties of metals. However, the development of these technologies into their modern forms is a testament to scientific advancements in the 19th and 20th centuries. The discovery of electromagnetic induction by Michael Faraday in 1831 laid the foundation for induction heating. Early applications of induction heating emerged in the late 19th century, primarily for melting metals. The first induction furnaces were developed in the early 20th century, revolutionizing metal casting processes. Heat treatment has an even longer history, dating back to ancient civilizations. The blacksmith's forge, where iron was heated and hammered to alter its properties, represents an early form of heat treatment. The development of metallurgy and a deeper understanding of the relationship between microstructure and properties led to more sophisticated heat treatment processes. The advent of World War II spurred significant advancements in both induction heating and heat treatment. The demand for high-strength materials for aircraft and other military equipment led to the development of new heat treatment processes and a deeper understanding of material science. Section 9. Future trends in induction foundry and heat treatment. The fields of induction foundry and heat treatment continue to evolve, driven by advancements in materials, science, automation, and Industry 4.0 technologies. These trends promise to enhance efficiency, precision, and sustainability in manufacturing processes. One significant trend is the increasing adoption of computer simulation and modeling in both design and process optimization. By simulating electromagnetic fields and heat transfer phenomena, engineers can optimize coil designs, heating parameters, and quenching processes, reducing trial and error, and improving overall efficiency. Another trend is the integration of artificial intelligence and machine learning into control systems. AI and ML algorithms can analyze vast amounts of process data, identifying patterns and anomalies to optimize process parameters in real time, further enhancing precision and reducing defects. Additive manufacturing, also known as 3D printing, presents both challenges and opportunities for induction heating and heat treatment. The ability to create complex geometries with additive manufacturing necessitates the development of new heat treatment techniques to ensure uniform properties throughout the component. Furthermore, there is a growing emphasis on sustainability in manufacturing. Induction heating and heat treatment, already considered relatively clean technologies, are poised to become even more environmentally friendly with advancements in energy-efficient power supplies and the use of renewable energy sources. The future of induction foundry and heat treatment is bright, with continuous innovation and technological advancements shaping the industry. These advancements will undoubtedly lead to novel applications, improved material properties, and a more sustainable future for manufacturing.